All right, welcome to stats, your stats practice assignment that you're going to do over the summer. I'm going to kind of walk you through how to do this, and then there's going to be several unknown data sets that you're actually going to have to analyze yourself. And then lastly, you're going to have to come up with your own experiment and also a data that goes along with it. You don't have to do the experiment and collect the data, but you want to come up with some data that kind of rationally makes sense in your mind, and then you're going to actually analyze it using the appropriate test. Okay, so the first set of data that I have here is actually the same exact data as the fertilizer example I gave you on the PowerPoint. We have our control information, fertilizer 1, fertilizer 2, and fertilizer 3. And hopefully you remembered that at the end we said fertilizer 3 was probably the best fertilizer and the most effective because there was less spread in the data. Fertilizer 2 had the highest mean, but it has so much more spread. So thus it's not quite, the data we collected may not be a reliable source. These could be anomalies. This could be an anomaly. We don't know. So the first thing we're going to do, I want to give you a little tutorial about how to actually use Excel. The first thing we're going to do is we're going to calculate the mean. Now, normally what you do is you take your calculator, type all those in, and add them together, and then divide by the total number, in this case, which is 5. But what's really neat about Excel, or in this case, Google Sheets, it does the same thing, is you can actually type in functions yourself, and it'll do them automatically by just clicking and dragging. So let me show you what I mean by that. So if you ever wanted to just add something, now I'm going to pretend this isn't going to be the actual mean. I'm going to just add it together. All you have to do when you want to put a function into a cell is hit equal. Then what you start to do is you type in the name of the function that you're trying to accomplish. So let's say we want to add them together. That is actually called sum, because sum is adding together. And then you get this information down here, and what you have to do is you click and drag and highlight all of the things you want to add together. So if I want to add all those together, I do that, I hit enter, and that adds them all together for me. If I want to then take the mean of that, I can do the sum and divide it by pressing slash by 5, because there's 5 data points, and that would be the mean. Okay, or you can skip the sum step, and instead, if you want to find it, you type in average, highlight the data points, go away, highlight the data points here, get rid of that. It always has to say equal first. Click there, highlight the data points, hit enter, and it gives me my average that way. What's even better about Excel is that you can actually, instead of having to do this over and over again, it's now going to assume that I'm going to apply this, if I click and drag, to the next one. There's our average for fertilizer 1, fertilizer 2, and fertilizer 3. You can click and drag. If you want practice doing it with each one, feel free to do that, but the click and drag method is the easiest. So now I've calculated the mean for each one. The next thing we're going to do is calculate the standard deviation. Now you could actually type in and actually do the whole thing based on the actual standard deviation equation, or you can do it by just typing in ST, this one, STDEV, and it will calculate the standard deviation of this sample for you. Now remember, the purpose of a standard deviation, what that means is we take our mean, and it kind of tells you that based on our sample size, all data points will fall within 1.06 or 1.07 approximately from the mean. So in this case, I would think it was centimeters. So that means this would, in this case, 68% of the points would fall between about 6.84 and 4.84, where 95% would be 2 standard deviations from the mean. Okay, so we can click and drag, and you get these values. And notice the values that we have here. Fertilizer 1 and fertilizer 2 clearly show that they have more spread or variance in their data. okay, or variation. We didn't actually calculate variance, we just did standard deviation, but it's a kind of a similar thing that we're looking for. It measures spread. Fertilizer 2 has tons of variation, and notice how high the standard deviation value is compared to fertilizer 3, which is just plus or minus 0.709. Okay. Now to calculate the standard error, all it is you take the standard deviation and you divide by the square root of the total number of individual points. So you're going to hit this equals, you're going to click that, okay, which is the standard deviation, you're going to divide it by, and then this is a little bit more complicated, the square root SQRT of 5. Hit enter. And there you get your standard error. Again, click and drag it. Notice again, you're still seeing a similar thing. It's a little bit different value, but the ones that have the highest spread also have the highest standard error. What we'll usually do with standard error is we'll create error bars on our graphs, and if they overlap, that means that those, we can't really say that they're statistically significantly different. And what we always do in science is we want to use 2 standard errors from the mean. So what I'm going to do is I'm going to hit equals 2, and then times, which is shift and 8, it's a little star, put a bracket around it, and click your standard error, and hit enter, and that's just multiplying the standard error by 2. Click and drag, and it does it for each one. Okay, so now what we can actually do is we can create a graph of the means, just like we did last time. That you've seen the graph created for this already, but I'm going to show you really quickly how to do that. We just want a graph of the means at this point, so we're going to highlight those, and we're going to hit insert chart, click that, and this looks like a good chart right here. You can create different types of charts, but this looks like a good one. Like you can click here, you can customize the charts as you want, but this is fine. This is the easiest one to do, and then X out of it. You can also include information about X and Y axes on there. Oops. Let me do that again. Insert chart. I think it's too zoomed in, isn't it? Zoom out here. Insert. And here's our chart of the 3 different data points right there. There's clearly a break in the data, but you can see what we have here. Now what you have to do is you have to put in your 2 times the standard error bars. And the way you're going to do that is, let's see, what's this here? I'm actually going to copy and paste this into copy. We're going to go to insert, and we're going to go to drawing. And we're going to put this image in our drawing. Okay, you can make it a little bit bigger so we can see it. And what I want to do is kind of put in my error bars, and this is just going to be an approximate thing. When you try to do the actual error bars that are on it, it's a little bit more difficult. So let's start with the first value. The first value is a 2 times standard error of 0.954, and our value is, our mean is 5.84, which is right here. So what you have to do is plus or minus 0.95 approximately on there. So we can calculate that. You can calculate it on your calculator at home. I'm going to do it real quick right here. Where's my calculator? I have to search for it. Okay. So if we do 5.84 plus 0.954 approximately, you get 6.79. So what we're going to do is when we want to draw our line here, you're going to actually create right in the middle, you're going to go up to about 6.79. So 7.5 is right here, halfway between 6.25 and 7.5 is probably about, 6.75 is probably right about there. It's not a perfect line, but it's fine. So remember, this is just going to be kind of approximate. And then you're going to do minus that value as well, and it's going to kind of go beyond that graph here. I'm just going to draw it in like that. That's horrible. Okay, like that. Next thing you're going to do is you're going to do it for the next value. Now, you can need huge ones for this. So 3.28. So you're going to take, if you look here, we have 3.28 and the mean is 7.74. So we take 7.74 and add 3.28 to it. You get 11.02. Now you're going to actually go beyond the graph space here, which is fine. It's going to be something way up here. Oops. Approximately. Again, this isn't going to be super accurate. I'm just doing it to show you kind of the point of these things. And then minus that value as well. It's going to go way down to probably about here. Now notice, these are not statistically significant. Why? Because we have overlap in the error bars. For number 3, our 2 times the standard error is 5.48. This is going to be huge. So it's basically going to go it's going to be way down here. And this one has the most spread. I'm just approximating this now. Remember, you just add and subtract 5.48 from the value. Oops. And up here, so there's tons of overlap here as well. If I had a mouse that wasn't from 1902. Okay, it's going to go way up here. Even higher probably. But then let's do the last one. And my computer's freezing. Too much for it to handle. Just hit save and close for a second. Like that. I'm going to add this again. I'm going to edit the drawing. Okay. Okay, so for the last one, I'm going to move the drawing over so we can see everything. Remember, the mean is 8.74, but our standard 2 times the standard error is only 0.63. So if we do that, we go 8.74, 8.74 plus 0.63 equals 9.37. So all we're going to do for this one is we're going to go up to, what was it again? 9.37, which is somewhere around, probably right around here. Okay. And then minus that same value. Again, I'm just approximating it right there. Now notice, there's only one of those fertilizers that does not overlap with the control. It's fertilizer 3. And remember, we said that that's the one that's most likely to be the one that's the best working fertilizer. And in this case, the data, we visualize it and it actually tells us that. Okay, so that's how the error bars kind of work. Remember, we always use 2 times the standard error to do that. So there's our chart or graph, our bar graph that we created with that. The next thing we're going to do is now the bar graph alone is not actually enough information. We have to actually get a statistical number. And we talked about t-tests before. And t-tests, basically, we're going to get a p-value. Usually get a t-value first, but this actually just spits out a p-value for you, which is basically the probability that randomness could explain our results. Okay, so if one of the ways we always improve experiments is we increase sample size. The bigger the sample size, the less chance that probability, or you kind of strengthen the chance that probability couldn't explain the trend that you have. So that's why it's always good to increase your sample size. But for a t-test, all you have to do is this. You hit equals, you hit t-test, okay, and then you highlight the 2 different data sets that you want to have. Oops, data set 1, comma, and then we highlight our next data set, 2. Don't include the means. Close your parentheses. Oh, and then you have to do this. It talks about the number of tails and type. We'll do a 2-tail because the 2-tail has the highest percent. It's a stronger test. And then 1, which is the type. You hit enter. And you get a value. This is your p-value. Okay, that's your probability value. That means that there's a 27% chance that randomness could explain those results. Remember, our threshold in science is that there's less than a 5% chance, a 5% chance or less that randomness could explain it. So that shows that the control and fertilizer 1 effectively are not statistically different, at least significantly different. Okay, let's try the control versus 2. It's the same thing. You hit equals and you do t-test, t-test, close parentheses. I think that's right. Let me highlight. Oops, I want to do this one. Highlight that, comma, highlight that, comma, do 2, tail, 1. Type 1, close parentheses. Duh, I did the wrong one. We got to do fertilizer 2. So let me show you how, if you make that mistake, let me show you fix it. Just erase that, highlight the one you actually want, hit enter. Okay, notice the higher value, but there's still a lot of spread. Again, there's a 23% chance that randomness could explain these results. Let's try number 3, equals t-test. And we'll do control, comma, fertilizer 3, comma, 2, 1. And now we get a value of 0.002. That means that there's a less than a 0.2 or about a 0.3% chance that randomness could have explained those results. So we see it over here, the visualization of the data, that it's different, right? Because there's no overlap in the error bars. And we also see, based on a statistic that we did, that our p-value is less than 0.05, meaning that it actually is statistically different. Okay, so that's how you would do and analyze your data using a t-test. Now we have another thing called an ANOVA, which I talked about briefly. That would actually be better at analyzing this because we have 3 different fertilizers to analyze instead of having to do this separately. But don't really worry about that. You're not going to have to do anything like that when you actually analyze any of the data so far. Okay, so there's that. If you have any questions on it, please, again, feel free to email me. The next data set that we have is our chi-squared data set. Now, when we do a chi-squared analysis, what it is used for is to compare observed results that we get versus expected results. And it usually does this based on like accounts data. Like we get a tally of the number of times something happens, or a tally of a number of things in a certain place, okay, based on categories or something like that. So a good example of this would be rolling dice. I used the coin example on the PowerPoint, but dice would be another example of this. There are 6 sides on the dice. 1, 2, 3, 4, 5, 6. And let's say we roll it 36 times, and when we did it, we observed these results: 7, 5, 4, 8, 6, 6. Okay. Now, how many times would you expect it if probability ruled, just strictly probability? How many times would you expect to roll the dice, or roll each side? Well, out of 36, and there's 6 dice, 36 divided by 6 different sides would be 6. So we're going to put 6 in each one of these. And what we want to do is we want to make sure that everything adds up. So remember, we're going to practice what we've done before, equals sum, parentheses, highlight the data. Okay, 36. And then I can actually click and drag, so it does the one below it. Both of them equal 36. Okay, you can click them to make sure that the data is highlighted that you want. All right, so now we have our observed dice values. So we're going to type them in. We get 7, 5, 4, 8, 6, and 6. Actually, I'm going to do something a little bit different. I'm going to do it like this. I'm going to put because I'm going to change these values just to show you what happens when you manipulate it. So I'm going to hit equals and then click B2. That means no matter what I put in there, it'll always be that. Equals that. And equals that. Okay, so now watch what happens if I manipulate this and I change this to 8. That changes to 8. Okay. For our expected, they're 6. I'm just going to type 6 all the way down. You can do that equals thing just like last time, or you can do it like that. And then we just can do our math, observed minus expected. So I'd do parentheses, 7 minus, which is just the minus sign on your keyboard, 6 close parentheses, enter. And you can click and drag so it does the math for you. Then you can square that value equals this cell, because we want to take this cell and square it. You do a caret and 2 to give you squared, enter, scroll down, gives you your values. You're going to divide that by the expected equals this divided by expected, enter, scroll down. Sum of all would be equals sum of all of these values, enter, and that's your chi-squared value, okay? 1.66666. What I am now going to do is I'm going to put up a chart, and I'm going to show you exactly how you determine what this value means, okay? So here's the chart. How many degrees of freedom do we have here? So degrees of freedom is the number of comparisons you are making, in this case -1. So we have 6 sides on the die, or the dice, so 6 minus 1 would be 5, so your degrees of freedom is 5. So we go to 5, and we go to our p-value of 0.05, and we go down and we see which value we have to be higher than. Okay? And notice that our value is much lower than that actual value that is there. And because that's the case, that means that we fail to reject the null hypothesis. The null hypothesis means that probability could explain our results. And if you actually look at our results, that seems feasible, right? If you roll a die 36 times, I could get a 1 7 times, a 2 5 times, a 3 4 times, a 4 8 times, etc., etc. That's completely within the realm of possibility. Now watch what happens to all of these values when I manipulate the data real quick. So we're going to make them out of control, and hopefully I can remember how to make them add to 36. We get 10 times a 1, okay? Then we get 2 here. Then we get 13 here. Then we get, gotta add those 25, get 8 here. 1 here. And get 2 here. All right. Now look what happens to our chi-squared value once we add them. We've now gotten way beyond, or way different than what we'd expect. And now our chi-squared value is 21. And if we go to the degrees of freedom at 5, now our value is way above that. So this is much less likely to be due to random chance. For some reason it's skewed towards getting more 1s and 3s and 4s as well, and against getting 2s, 5s, and 6s. Now, is it completely out of the realm of possibility? No, that can happen out of 36 rolls. But the chance of it being probability are very low. Okay, so that's how you do a chi-squared analysis. The last thing that I'm going to show you in terms of new things is a correlation. And this one is super easy. All you're going to do, now this is looking at ice cream sales versus temperature. Is there an effect on the temperature outside in degrees Celsius and how much ice cream is actually sold? So what we're going to do is, this is the easiest one. You hit equals and you go correl. And that's a Pearson correlation, which is basically it's going to give you a coefficient between 1 and -1. Remember, 1 means a perfect positive correlation, -1 is a perfect negative correlation, and 0 means there's no correlation at all. So we're looking for something like that. Now, what would you expect to get? You'd expect a higher ice cream sales when it's warmer outside. And let's see if, in fact, that's the case when we analyze the data. So you're going to highlight the first data set, comma, the second data set, okay? And you hit enter, and you get a correlation value of 0.958 about, or 0.96. Is that close to 1, -1, or 0? It's very close to 1. So that means we have a very strong positive correlation here, meaning that as temperature increases, ice cream sales increase. And what we can do then is we can actually create a chart for this. You go to Insert, and we're going to go Chart, just like we did last time. If you look at this, and you can actually create a best fit. Let's see, customization. You can put, this is where you'd put your titles in, right, and your different, and the axes. So if you do like the horizontal axis, that would be temperature, temp, in degrees Celsius and the, okay, and left vertical axis, we'll do ice cream sales in dollars. Okay, so that would have that there. Then what you can do is you can actually include best fit lines down here somewhere, add a trend line, add a linear trend line, insert. See how it has error bars? These error bars are not accurate, so don't ever use them to draw your error bars. And here is our result. So this definitely showed that there's a positive correlation. It's very close because most of the points fall right within the line. If they were scattered more around, you'd have less strong of a correlation. Okay, so I hope that helps. Now, the last thing is what you actually have to do yourself, because you've gone through this now and you've done practice using these different data sets. Now you're going to have to do these unknown data sets, and let me just show you them real quick and explain them. So here's the first one. It's actually an experiment on insect behavior, and this is similar to a lab that they've done, or a lab question they've put on the exam in the past. This experiment wants you to test the effect of darkness on the behavior of pill bugs. 70 pill bugs were distributed randomly throughout the terrarium that is diagrammed below. So here's the terrarium, okay, and the 70 were randomly distributed throughout the dark and the light side. One side of the terrarium was covered to allow almost no light in, and the other side was lit. All of the variables were held constant: temperature, moisture, etc. The following was the data that resulted from this experiment after the pill bugs were allowed to move freely from the terrarium for 10 minutes. Use the appropriate statistic to determine if there is a statistically significant difference between the number of bugs on the light side and the dark side of the terrarium. That should say 10 minutes, not 20 minutes. Okay? I'll probably change that on yours. All right. So remember, there's probably about 35 on this side and 35 on that side initially, because we evenly distributed them. So if there is no effect whatsoever, I want you to think about how many would be on each side. Okay, after 10 minutes, if they're just moving randomly. Okay, now you're going to try to do the appropriate statistic for this. If you need extra help, please feel free to email me. And I may have days that I'm going to come in August if anyone wants to meet me here, and I can help you with this. Okay, so that's the first data set. The second data set is this. The following is an experiment used to test the effect of synthetic testosterone on male body mass index. The control group, n equals 10, received a placebo 3 times a week for 10 weeks, and the experimental group, n equals 10, same amount, received the steroid 3 times a week for 10 weeks, which in this case was testosterone. The diets were held in a strict control, as were the workouts that they did, and after 10 weeks, the percent body mass gained was determined, and the results are in the table aside. So here's our results right here. Okay, there's our number of individuals in each group. That's the placebo group, that's the testosterone group. Negative percentages indicate a loss in mass. Use an appropriate statistical test to determine if there truly is an effect of testosterone on BMI. So now you're going to have to do, it's one of the tests that we've done. You're going to have to figure out which one of the tests that we've done. Either a t-test with the standard deviation and stuff like that, the chi-squared analysis, or a correlation would make the most sense in this case. Okay? And it's possible that you could even do, well, actually, no. In this case, it's not. There's only one test that you should be able to do it. Okay? The last thing that you're going to have to do is come up with your own. You're going to click in this box, as it says here, and you're going to replace this text with your own scenario. I want everyone to have their own. Don't copy. You can come up with similar experiments, but make sure the data that you have is different. And then you're going to analyze it using one of the analyses that we've gone over. Okay, so it can be similar to the ones we did, but I want it to be different, and I want you to kind of show me that you understand this process. This can be confusing, I understand that. This is not an easy topic to do, especially when you're trying to apply math as opposed to just memorizing how to do it. So again, if you have any questions, feel free to email me, and that's it.